All right, so let's get going on this penultimate class meeting for statistics. So today we're going to finish our look at Introduction to Statistical Analysis and Psychology by taking a look at a very useful and introducing a very useful hypothesis testing procedure known as an Anova, an analysis of variance. So to set this up, let's take a look at an example where an Anova would be appropriate. So in comparative psychology and animal psychology, researchers are interested in the behavior of animals. And one very curious thing that birds do, a very highly studied animal in psychology, is birds migrate. So some birds migrate, some birds don't. And when you take a look at migration patterns, they're astoundingly long, some of them, and astoundingly difficult for the birds to accomplish. So these aren't leisurely walks in the park. These are death-defying treks across, for some of them, the entire expanse of the globe. So the Arctic tern literally goes from the northern, all the way up in the northern hemisphere to all the way down in the southern hemisphere. That is the migration pattern of the Arctic tern. So some birds migrate these vast distances. Other birds, however, don't. So many birds are just able to survive winter climates, find food, and basically survive in this harsh environment. So why is it that some birds do not migrate and are able to survive and exhibit that behavior, while other birds migrate long distances and exhibit that particular behavior? So we're going to take a look at a study that took a look at that and tried to link it to bird intelligence. So is it possible that the intelligence of the bird dictates whether or not it migrates? In other words, a more intelligent bird will be able to survive in a winter environment, whereas a less intelligent bird has no option but to migrate in order to survive. So this was a study done by Saul and colleagues, and they took a look at brain sizes for birds that migrated different distances and used that as a measure of bird intelligence. And we're going to see the type of statistics that they ran to see if it actually is birds with bigger brains, birds that are more able to plan and remember things that don't migrate, whereas birds with smaller brains do migrate. And just to give you an indication of the abilities of some of these birds, I used to, when I was in doing my master's, one of the professors that I worked with, she did studies on bird memory, and they would do studies with finches, for example, where they would hide food in hundreds of different locations. So they would have these tubes, and they would literally have thousands of tubes, and they would hide food in hundreds of locations, and the birds would find the food and memorize where the food was. What they would then do is they would move half of the food to see if the birds would then go back to the original locations, indicating that they remembered where the location was, or would they go to the new locations, indicating that they were using maybe a sense of smell to locate the food. And what they found was that the birds went to the old locations and could literally remember hundreds of specific locations where they hid their food. So bird brain should not be an insult. It should be a compliment for awesome memory. But regardless, why do some birds migrate? Why do others not migrate? Why do they migrate different distances? We're going to take a look at how Saul and colleagues analyzed this with the introduction of the Anova. So we're going to introduce the idea of the Anova first. We're going to give you the logic behind the analysis of variance so we understand the nuts and bolts of this procedure. And that will be it for our initial introduction to what is the Anova and what is it all about. All right, so far we've been dealing with hypothesis testing situations that were only ever looking at two populations. They were only ever testing between two populations. So the population of monkeys that prefer the terry cloth mother versus the population of monkeys that prefers the wire mesh mother. the population of monkeys, it wasn't all monkeys. The population of people asked how fast were the cars going when they hit each other versus how fast were the cars going when they smashed into each other. So far, it's only been 2 populations that we've been using a hypothesis test to distinguish between. And we would take samples from those 2 populations, and then depending upon the design of the experiment, we would either do a single sample t-test, a dependent means t-test, or an independent means t-test. And while this is very helpful for a large number of psychology questions, it doesn't cover all of them. Because sometimes you want to be able to compare 3 populations. You want to be able to compare 3 different conditions, sometimes even more than 3. So how is it that we can compare 3 conditions or more and do that in a fair and objective manner? So if we're in this situation where we have a sample from 3 different populations and we want to test whether the populations are different, let's reorder those populations so we got them in order 1, 2, 3. What is it that we need to do in order to do this hypothesis test? Take a look at the samples and determine whether the populations are different. Well, we're going to start off with what we can't do and why we can't do it to show you why the Anova needs to exist. So you might be sitting here thinking to yourself, well, we're able to do t-tests. We're able to compare 2 samples to each other. So couldn't we handle this situation just by doing a t-test and comparing sample 1 to sample 2 like we've been doing this entire time, and then see if those 2 are different, and then follow that up with another t-test between sample 2 and sample 3 to see if those 2 populations are different, and then complete the analysis by comparing sample 1 to sample 3 to see if those 2 populations are different. 3 t-tests, and you would be able to tell by pairwise comparison which of these populations are different. So you might think that that is something we can do, but in fact it turns out this is wrong, and it leads to errors, and it violates assumptions, and it's not a correct way of analyzing this situation. So what's the problem with making these multiple comparisons? Right? In this situation, we would have to make 3 comparisons in order to complete our hypothesis test. Normally, we've only been doing 1 comparison. So what's the problem with making multiple comparisons? Well, the problem is that it inflates your experiment-wise alpha level. So the alpha level that we chose, that's a very special number. That is the probability that you are willing to find an effect even when there is no effect there. It is your willingness, is how risky you are allowing yourself to be, that you might make an error and say that there is a difference when in fact there isn't a difference. And if you take a look at alpha levels across the sciences, across psychology, you'll see this reflected in the alpha levels. So for example, for most of psychology, such as the psychology that I do, where we're taking a look at pictures and we're trying to understand metaphors, if I say that there's an effect when there isn't actually an effect, it's not going to be too detrimental. Nobody's going to get injured. Nobody's going to lose their quality of life. So I can choose a p-value, I can choose an alpha level of 0.05, which is basically saying I'm willing to take a 5% chance that I'm going to say, oh, there's a difference between these 2 populations, when in fact there isn't. And that's pretty much as low as, as high as psychologists will go. If, on the other hand, I'm doing something like cognitive behavioral therapy, where I'm dealing with mental health issues, it would be way worse if I said that a treatment worked when in fact it didn't work. So in that case, 5% might be too much of a risk. So I will say I'm going to choose an alpha of 0.01%, right? So that I reduce the risk of saying that the treatment is effective when it's not. And if I was doing maybe cancer research, where I was dealing with treatments that could be lethal if I make that error, I might set my alpha rate at 0.001 and just have a 1 in 1,000 risk of potentially making that error. So you want to control your alpha, and specifically you don't want your alpha to balloon. You don't want your alpha to get out of control. So your alpha level can be broken down into your experiment-wise alpha level, which is the alpha level for the entire experiment, your chance of making an error in your entire experiment, versus your test-wise alpha level, the chance of making a mistake for each individual comparison. So that type 1 error is what it's called. It's the probability of saying that there's an effect when there actually isn't any effect. And your test-wise alpha level is the alpha level for each comparison. Your experiment-wise alpha level is the accumulated alpha level, the ballooned alpha level, if you will, for all your comparisons. And as you can see, so far, our test-wise alpha level has always been equal to our experiment-wise alpha level, because up until this point, we've only been doing one comparison. So the comparison, the alpha level for each comparison was the accumulated alpha level for all comparisons, because we only had the one comparison. All right, so this accumulated type 1 error, that's what we want to control. That's what we want to keep at our selected alpha level. So what happens in that case when you make multiple comparisons? Well, let's consider that we have a test-wise alpha level of 0.5, 50%. So let's say that our statistical software that we're using is actually just flipping a coin. And if it comes up heads, there's no effect. If it comes up tails, there is an effect. It comes up heads, you accept the null hypothesis. It comes up tails, you reject the null hypothesis. That would be a horrible statistical package, but it's a nice way to illustrate this issue. So we're just going to flip a coin, and let's suppose that there is no effect. Let's suppose that there is no difference between these three populations. What is the probability of making at least one type 1 error? What's the probability of saying that there is an effect even when there is no effect after one test? Well, after one test, let's say between these two right here, we flip that coin. Heads, we get it correct, and we say that there's no effect. Tails, we get it incorrect. We say that there is an effect. There's a 50-50 chance, so we got a 50% chance of making an error. So after one comparison, we have a 50% chance of making an error. And that's okay, because that was our test-wise alpha level that we set. We set a test-wise alpha level of 50%. So far, so good. The problem arises for the next few comparisons. So that's after one comparison. What is the probability of making at least one type 1 error, saying that there's an effect when there isn't an effect, after two tests? Well, that starts to accumulate, because not only can you make an error on the first test, you also have a second chance to make an error on the second test. So you can make an error on the first test, you can make an error on the second test, you can make an error on both the first and second test. There's only one way that you will not make an error, and that is a 50-50 chance of getting it right the first time and a 50-50 chance of getting it right the second time. Accumulated, those probabilities mean that you now have a 75% chance of making one type 1 error. 75% chance of saying that there is an effect when in fact there is no effect. And this is a problem because we wanted an alpha level of 0.5. That was the amount of risk we were willing to take. Now all of a sudden after two tests, it's ballooned up to 75%. And you can imagine what happens after three tests. So for the third test, we once again flip that coin. Once again, we have a 50-50 shot of making an error. There it is right there. So the probability of at least one of these coming up tails, the probability of at least one of these coin flips causing us to make an error has now gone up to 87.5%. So we were planning on having a risk level, an alpha level of 0.5, but after three tests, that risk level has ballooned to 87.5. All right, so far so good? Okay, so let's consider a better test-wise alpha level, one that psychologists actually use Let's take a look at what happens with 0.05. So this would be like flipping a really, really unfair coin, where you got a 95% chance of getting heads and a 5% chance of getting tails. So once again, suppose that there is no effect. Suppose that there is no difference between these populations. What's the probability of making that error, that type 1 error, after one test? Well, once again, we've been in this situation. We have one comparison, we flip the coin once, and we got a 5% chance of saying that there's an effect, when in fact there is no effect. And that's fine because that's the alpha level that we chose. You always have to choose a certain amount of risk for making an error whenever you're doing statistics. So that's fine. After one test, we're still good. What about two tests? Once you take it to two tests, your alpha level starts to inflate. It starts to get out of control. So after two tests, we have a 5% chance of getting it wrong on the first test. We got a 5% chance of getting it wrong on the second test. Taken together, that balloons up to a 9.75 chance of making at least one error. So we are now almost double our initial alpha level. And if we do three tests, the math works out to a 5% chance of getting it wrong 3 times. That means that we have now a 14.3% chance of getting it wrong. So while we were completely happy with an alpha level of 0.05, risking 5% that we might find evidence of an effect when an effect doesn't actually exist, now all of a sudden after 3 tests we're up to 14.3. And you can imagine what happens after 4 tests, 5 tests, 6 comparisons, which is something that can be often seen in psychology. So this is not just a hypothetical issue. There's actually a infamous article that was published back in 1964 that did this, incorrectly used t-test rather than an Anova. So they did an analysis of the MMPI, the Minnesota Multiphasic Personality Inventory, profiles of 40 college-educated overt male homosexuals. So they wanted to see, are there any personality differences between heterosexual males and homosexual males as revealed in this personality test? Well, this personality test is multiphasic, or phasic. What that means is that it takes a look at a lot of different dimensions to your personality. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 different dimensions in this test. And what they did was they ran, you can see it right there, they ran a t-test on all of these particular dimensions. Now, maybe not on the first 2, but they ran a t-test on those dimensions and they found significant differences. Specifically, they found significant differences for psychopathic deviant. They found a significant difference for masculinity, femininity, and they found significant differences for schizophrenia and hypomania. So these were higher in the gay sample than they were in the heterosexual sample. And you can see, you can see that they are, let me back it up here, that those were the ones that were significantly different. However, they made multiple comparisons. So while they think that this probability is 0.05, while they think that that probability is 0.01, those multiple comparisons ballooned their alpha level so that these comparisons are highly likely to have been errors, highly likely to have been different just by chance, and they increase the probability of making at least one error. So that is one of the reasons why these came out as significant. So further research has been done on this. These differences turned out not all of them turned out to exist, but importantly, they found differences where no differences existed because they did multiple comparisons. All right, so we can't do multiple comparisons, so we need a method, though, of making these multiple tests, because especially in psychology, a lot of our characteristics, a lot of our causes of behavior don't fall into just 2 values, right? They don't fall into those nice, neat dichotomies. So we need a way to make multiple tests. So this is where the Anova comes in. This is where the hypothesis test that we learned today will apply. So an Anova is one test with one alpha level that can evaluate multiple samples all at the same time. So it gets around this multiple comparisons by doing one comparison, one overall comparison of all your samples in just one single test. So how does this Anova work? Well, before we get into that, we just got to be clear on a little bit of terminology here. First thing that we need to know about is the term factor. Factor is your independent variable or your quasi-independent variable. This is your cause of behavior. This is basically what determines what your samples belong to. So, for example, type of mother in the infant attachment experiment was a factor. Type of question in the Loftus and Palmer memory study was a factor. Amount of timeout in the timeout study was a factor. These are the causes of the behavior. Levels for each factor are how many individual conditions make up each factor. So in the infant attachment studies, there was two levels. There was a wire mesh mother and there was a terry cloth mother. If we added a third mother, if we added a silly putty mother, then we would have three factors. So the factors are how many values can your variable or does your variable have? All right, so once again, for the infant attachment studies, we were looking at one factor, type of mother, and we were looking at two levels, wire mesh versus terry cloth. One factor with two levels, that's a t-test. You can do a t-test in that situation, and it's the correct test to do. For this example here, we didn't see this one yet, but we'll go through it. When people learn a new task, their performance usually improves when they are tested the next day, but only if they get at least 6 hours of sleep. The following data demonstrate this phenomenon. The participants learned a visual discrimination task on one day, and then were tested on the task the following day. Half of the participants were allowed to have at least 6 hours of sleep, and the other half were kept awake all night. So in this case, we're looking at sleep deprivation. That is your factor, the amount of sleep. And in this case, there's two levels. You either got 6 hours of sleep or you got no sleep. So once again, this would be a t-test appropriate hypothesis analysis. All right, Strack, Martin, and Stepper reported that people rate cartoons as funnier when holding a pen in their teeth, which forced them to smile, than when holding a pen in their lips, which forced them to frown. This is a test of one of my favorite theories in psychology. It's called the facial feedback hypothesis. This is the hypothesis that we read our emotions off of our faces, and that we have a physical reaction to any particular situation, like laughing, and then our brain looks at our face, reads it, and says, oh, we must be happy because we're laughing. So it's a completely counterintuitive reversal of what people thought. We don't smile because we're happy because we smile. And that's part of the reason why a lot of treatments for mood disorders will have physical aspects to them. So, stand up straight, shoulders back. It just makes you feel better because your mind is reading off of your body. Anyways, in this study, they tricked people into smiling, or they tricked people into frowning by holding a pen in their lips, in their mouth, and then they saw if they rated cartoons. And a researcher attempted to replicate this result using a sample of 16 adults between the ages of 40 and 45. For each person, the researcher recorded the difference between the ratings obtained while smiling and the rating obtained while frowning. So in this case, once again, we have one factor, which is the facial expression, and we have, once again, two levels, smiling versus frowning. So this would be another example where it would be appropriate to do a t-test. However, let's say that we wanted to expand on this work. And let's say that we wanted to test or investigate whether these effects of facial expression, whether they work the same in children versus young adults versus older adults. So in this case, we would redo the experiment, and we would have children holding the pen in their mouths, either smiling or frowning, adults, young adults, holding the pen in their mouths, either smiling or frowning, and then older adults holding the pen in their mouth, either smiling or frowning. In this case, we have two factors, two potential causes of behavior. One is facial expression, and the other one is age. So we're testing the effects of facial expression, and we're also testing the effects of age. So this is the first situation where we would have two factors. For factor A, facial expression, we got two levels. We have smiling versus frowning. For factor B, we have three levels. We have children versus young adults versus older adults. So in this case, for this experiment here, you could not do a t-test because that would require multiple comparisons. That would inflate your experiment-wise error rate. As soon as you go beyond one factor and or have any factor that has three or more levels, you have gone beyond what a t-test can do, and you now get into ANOVAs. So what we're going to do is, because this is your introduction to statistical analysis in psychology, we're going to introduce and start with the simplest ANOVA. And that's where we're going to end this course. We're just going to take a look at a single factor independent measures design when we're introducing ANOVAs. On your next stats course, maybe in grad school, you will expand upon this, but that's what we're going to be doing to round out this course. So what this means, it's single factor, we got one factor, we got one cause of behavior. However, now we can have as many levels as we want. So we can have 3 levels, 4 levels, 5 levels, 12 levels. Doesn't matter how many levels, you can do an ANOVA with it. So we have one factor with as many levels as we want. The logic behind the hypothesis test is going to be exactly the same as what we've seen before. Just a couple of small little differences. First one starting with the hypotheses. So for an ANOVA, the null hypothesis is that every single population has the same mean. So population 1 is equal to population 2, population 2 is equal to population 3, population 3 is equal to population 4. Every population is equal to each other. So one of the first things to notice in ANOVA is that it's basically a two-tailed test all the way through, right? We're looking at a null hypothesis of everything equals everything else. Every population equals every other population. That's your null hypothesis. Your research hypothesis is slightly different. It's expressed as an English sentence rather than a mathematical function. And what it says is that at least one population mean is different from another. So it is saying that at least one of these populations is different. And that at least one is very important because it might only be one that is different. It could be 2 that are different. It could be 3 that are different. It could be all of them that are different from each other. But the research hypothesis says at least one of them is different. So once again, we have the complete opposite of the null hypothesis. Null hypothesis is that they're all the same. Research hypothesis is that at least one of them is different. Maybe all, but at least one. Now this is written out in English this way because writing this out mathematically can get very, very difficult. So if I wanted to express this, the opposite of this as a null hypothesis mathematically, I would have to write that our research hypothesis is that the mean of population 1 does not equal the mean of population 2, and or the mean of population 1 does not equal the mean of population 3, and or the mean of population 1 does not equal the mean of population 4, and or the mean of population 1 does not equal the mean of population 5, and or the mean of population 1 does not equal all the way up to the final population, right? Because it could be 1 or all of these. And then you get to start again with the mean of population 2 does not equal the mean of population 3. The mean of population 2 does not equal the mean of population 4. The mean of population 2 does not equal the mean of all the way to the final population. And then you start for the population number 3. And you can see that it's going to take a lot if you go beyond 5, 6 populations. So just to make it easier, we just write at least one population mean is different from another. And that's your research hypothesis. All right, so we have our research hypothesis. We're going to go through the steps when we do an Anova live in the second part of today's class. But for right now, we're going to discuss what is the test statistic for the Anova. So just the same way that your t-test had a t-statistic, your Anovas also have a test statistic. It works like a t-statistic, but it is a little bit different. So we have our t-statistic here, and in general, we get the difference that we have between two sample means, and we divide that by the standard error, which is how much difference we could expect. So that in general is your formula for a t-test. What's the difference that you got versus what's the difference that you expected? And if that t-statistic is large, chances are you have a significant difference between your populations. The statistic for the Anova is like a t-statistic, but instead of means, it uses variances. So it's called an F statistic, and it uses the variance between sample means, and it divides that by the expected variance. So once again, we're dividing what we got by what we expected, but this time it's the variances that we have between the samples versus what we would have expected just by chance. So that's the F statistic, and we're going to break it down and see exactly where these variances come from, because that will come up in our analysis of the Anovas. So let's say that we have these samples, 3 samples from 3 different populations. So this is one factor with 3 different levels. And we have the following scores. So in sample 1, we tested our subjects and they got a score of 01310. In sample 2, we tested our subjects, they got a score of 43634. And sample 3, we tested our subjects, they got a score of 12200. So sample 1 has a mean of 1, sample 2 has a mean of 4, sample 3 has a mean of 1. In this experiment, there is variability between the scores. And that is what an Anova takes advantage of. An Anova is an analysis of variance. So it's going to analyze the variability, the variance in this experiment. So what variance are we actually analyzing? Well, as it turns out, you can break variance into 3 major categories, 3 major components. The first one is the total variance. So the total variance is the variance for all of your scores. It is the variability amongst every single subject in your experiment. So this subject scored a 0. That is different from this subject who scored a 1. That's different from this subject who scored a 3. That's different from this subject that scored a 6. They're different from this subject that scored a 0. There's variability across all of the subjects. That is the total amount of variability in your experiment. That is the total amount of variance in your experiment. That's total variance. That's as variable as your answers get. Now that total variance can be split up into subsections, different parts of variability. So the first one is between treatments variance. And between treatments variance, this is the variance among the treatment means. And what that is you take a look at the treatment means right there, and you'll notice that they're not the same. They are different. One of the means is 1. The other one is 4. The third one has a mean of 1. Those are different numbers. That has a certain amount of variability. That is your between treatments variance. So this is the amount of variability between the treatments. And that's one component of total variance. The other component is within treatments variance. And that is the variance within each sample. So if we go here to sample 1, and we take a look at the scores that the subjects had in sample 1, they're different, right? Subject 1 scored 0, subject 2 scored 1, subject 3 scored 3. Those are different numbers. There's a certain amount of variance in that particular sample. We take a look at sample number 2. Those scores are different. There's a certain amount of variance in that particular sample. We take a look at sample number 3. Those scores are different. So there's variance within that sample. So within treatments variance is how much variability is occurring within each sample. All right, so now we got total variance, we got between treatments variance, we got within treatments variance. So why did we bring that up? Well, as it turns out, through a little bit of math magic, total variance equals between treatment variance plus within treatment variance. So the variance for the entire experiment equals the variance you have between the sample means plus the variance you have within each sample. And an Anova takes advantage of where the between treatment variance comes from and where the within treatment variance comes from, because they come from different sources. So they can be used to measure those different sources. So where do these variances come from? Well, between treatment variance, that measures differences that are due to treatment effects, and it measures differences that are due to random variation. So between treatment variance is caused by treatment effects and any random variation. So let's take a look at these numbers here. So let's focus on samples 1 and 2. Sample 1 has a mean of 1. Sample 2 has a mean of 4. That difference between 1 and 4 could be due to the treatment that sample 1 received versus the treatment that sample 2 received. So it could be due to an actual treatment effect, right? The drug that we gave sample 1 does not work as well as the drug that we gave sample 2. It might be due to treatment effects, but it could also be due to random variation, right? It could be due to the fact that this subject and this subject, maybe they just didn't get sleep the night before. Maybe they were just having an off day. Maybe any one of 1,000 different reasons could attribute to their poor performance other than the treatment. So maybe they were sleepy, maybe they were scared, maybe they were thinking about an important meeting that they have later in the day. Whatever it was, it could also be due to random variation from each of the subjects. So your between treatment variance could either be due to the treatment and or it could be due to random variation. So it's got two possible sources, treatment effects and random variation. Your within treatment variance, that is going to measure the differences, and this is the important part, of random variation and only random variation. So that measures how much random variation you can expect. So let's take a look here at sample number 1. Sample number 1 received the same treatment. So if this was a drug experiment, if this was drug trials, sample number 1 all received the same drug. So any differences in their scores cannot be due to that drug because they all received the same treatment. They all received the same drug. So there's no treatment effects possible inside sample 1. Any differences we see in this sample is due to random variation. That's the only source. So it's due to the fact that subject number 1 didn't get enough sleep. It's due to the fact that subject number 2 has a sensitivity to gluten. It's due to the fact that subject number 3 really tries their hardest in every single experiment. It's just due to random variation. So these differences in a sample can only be due to random variation. Same thing with sample number 2. They were all treated the same. They all got the same treatment. Any differences that we see has to be due to just the fact that humans are random variable creatures a lot of the times in their behavior. So that's where within treatment variance comes from. So now we have a number for between treatments variance that comes from treatment effects and random variation. We can also measure how much within treatment variance is. That's treatment just due to random variation. And then we can calculate our F statistic that looks at how much did we find between the samples and how much variance could we have expected. So the F statistic turns out to be, the F statistic, you can see it as the variance between sample means, this between treatments variance, that could be due to treatment effects or random variation. That's going to cause differences between your samples. Your expected variance, that is just random variation. So your expected variance is only due to random variation. That's how much variation you would expect if there was no treatment effect. And as it turns out, we can measure those by the top is your between treatment variance, as we can see here, and the bottom is your within treatment variance, as we can see here. So treatment effects and random variation, that's between. Random variation on its own, that is within treatment variance. So the last thing we want to take a look at now is, what does your F statistic kind of indicate? What does it mean? So let's take a look, and we'll analyze first if there is no treatment effect. So let's say that the truth of the matter, the truth of your treatment is that it doesn't work. Your treatment does nothing. It's ineffective. It has no treatment effect. In this case, your treatment effect is going to be 0. That's the definition of no treatment effect. Your treatment does nothing. Your treatment equals 0. So we can substitute in 0 for treatment effects up here. So we plug that in, 0 plus random variation divided by random variation. So we're just plugging 0 into the F statistic formula. And what we end up with is random variation divided by random variation. And if you remember your algebra, anything divided by itself is going to equal 1. So when there is no treatment effect, you will get an F statistic equal to 1 or very close to 1. So the closer you have, the closer to 1 your F statistic is, the more likely that there is no treatment effect, right? Because you end up with random variation divided by random variation, that gives you an F statistic of 1. So that's if there's no treatment effect. What if there is a treatment effect? What if your treatment actually does something? What if your treatment actually, has an effect? Well, in this case, then the treatment effect is greater than 0. Saying that there is a treatment effect means that your treatment effect is more than nothing. It's greater than 0. So once again, we can sub that in to our formula. And we'll say that the treatment effect, we'll represent it by the variable x. Right? So x is the amount of treatment effect. Let's split up that numerator there. So we have x divided by random variation plus random variation divided by random variation. Now, we don't know what x is here. It's some amount of treatment effect. We know that it's positive. But we do know what random variation divided by random variation is. That is equal to 1. So random variation divided by random variation is equal to 1. This is equal to something. Something plus 1 will give you an F statistic larger than 1. So this has to be something. If there's a treatment effect, this is equal to 1. So if you get an F statistic greater than 1, that's an indication that you have a treatment effect. And as it turns out, much like the T statistic, F statistics have their own distribution. This is what an F distribution looks like. So you'll notice it's skewed. It's not symmetrical like a T distribution, but it works basically exactly the same. This is a distribution of F statistics that you would get if there was no effect. And much like we've been doing this entire time, we are going to choose a proportion of this distribution, a tail, based on our alpha level. That is going to create a cutoff score, a cutoff F statistic, where in this case, for an alpha level of 0.05, we got 95% in the body with the remaining 5% of the distribution in the tail. And we will calculate an F statistic. And if our F statistic is in the body, we accept the null hypothesis, we reject the research hypothesis, we say that there is no effect. But if our F statistic crosses over into the tail, then we accept the research hypothesis, we reject the null hypothesis, and just like we've been doing this entire time, if it gets into the tail, we reject the null hypothesis, we say that there is an effect. So in the end, the logic of the Anova works out to be basically the same as the logic of the t-test. It's just that the t-test looks at the differences between means, whereas the Anova looks at the differences between variances. And this allows you to do one test that takes care of your test-wise alpha level. All right, so that was your intro to the Anova. We'll take a 10-minute break right now, and then at 10 o'clock we will do an Anova live. So during the break, if you haven't already, fire up your SPSS and also open up the Excel sheet in the practice Excel sheets in Canvas. But other than that, let's take a break, and we will come back at 10 to continue this final class.